Hey ho, what's up, Logic class? Here I am. We're going to do another podcast. We're going to talk about predicate, logic, rules of inference today. So let's get started. So first things first, we got 5 new rules coming at you. We got universal instantiation, which will abbreviate capital U, capital I. Universal generalization, abbreviated capital U, capital G. Existential generalization, abbreviated capital E, capital G. Existential instantiation, abbreviated capital E, capital I. And change of quantifier, which will be abbreviated capital C, capital Q. So I'll go through each one of these individually, discuss how they work. We'll do a few small proofs with them, and then we'll call it a day. And then I'm going to do another video later on where I'm actually standing in front of the board again. Okay, so let's get moving. So universal instantiation in general. Here's a general rule for it. It's an operation that consists in deleting a universal quantifier and replacing every variable bound by that quantifier with the same instantial letter. So what it allows us to do is it allows us to remove a universal quantifier and replace every variable bound by that quantifier with the same instantial letter. A few examples will help to show. So let's look at it closer. So for example, let's say I have for all x, fx. We should be familiar with this by now, but that tells us that for all x, if x exists, then x is f. Every single x that exists is f. So for instance, if I want to universal instantiate, what I can do is I can remove the universal quantifier. Notice up here, follow my cursor, I have an all x, fx. Universal instantiation allows me to remove the quantifier and replace the variable, or I could have kept the same variable. If I wanted to, I could just have removed it and left fx there. In addition, I can remove the quantifier and change my variable to a constant. So remember, my variables are lowercase letters x, y, and z, and my constants are lowercase letters a through w. So note, we can replace the bound variable with either another variable or a constant. Another thing to keep in mind is that we can only use universal instantiation on statement functions that are bound by universal quantifiers. So let's take a look at an example. All guitarists are rockers. Jimi Hendrix is a guitarist. Therefore, Jimi Hendrix is a rocker. We may symbolize this as follows. For all x, if x is a guitarist, then x is a rocker. Jimmy is a guitarist, therefore Jimmy is a rocker. Now notice, premise 1, of course, you should be used to this by now. Since it's a universal quantifier, we've translated it as an implication. Premise 2 is a singular statement. Therefore, we use the capital letter G to stand for the predicate guitarist and the lowercase letter J for Jimmy. So our conclusion is a singular statement. Now, in order to do a proof on this, we're first going to need to universally instantiate line 1. And this is because our rules of implication cannot be used on lines that are governed by a quantifier. Since line 1, the entire statement function, if gx then rx, is bound by the quantifier, the universal quantifier here, we cannot use our rules of implication. So we're going to have to remove this quantifier in order to use our rules of implication. Now let's look. The first premise states that for any item x in the universe, if that item is G, then it is R. Since Jimi Hendrix is himself an item in the universe, the first premise implies that if Jimmy is a G, then Jimmy is an R. A line stating just this can be derived by UI. So universal instantiation provides us with an instance of the universal statement for all x if gx then rx. Let's look at it in an example. So here we go. For all x, if gx then rx, j is g, therefore j is r. First thing we got to do is we want to use our universal instantiation rule. So what I've done is I've removed the variable, or not the variable, pardon me, the quantifier from premise 1, and I've replaced the variables that were bound by that quantifier with the constant letter j. Now the reason I do that is simply because on line 2, my constant letter is lowercase j. This allows me to use our familiar rule of modus ponens. Now I could have changed the variable x from premise 1, this variable attached to the g and this variable attached to the r, to any letter I wanted to, or whatever variable I wanted to. But because on line 2 I have j, it makes sense for me to replace these variables with the constant j so that I can then use modus ponens. Now that I've done that, we can see that the problem is solved. Now let's take a look at what we call universal generalization. Universal generalization, in a sense, is it's the exact opposite of universal instantiation, but it does have some restrictions to it. So with universal generalization, what we can do is, for instance, look at my left here, I have an fy. Now remember, y's are variables. I'm allowed to add a quantifier, now a universal quantifier, hence the name universal generalization. So since I have an fy, I can claim for all x, fx. Now if I wanted to, I could have put for all y, fy. What I'm not allowed to do, however, is move from a constant to a universalized statement. So notice the red on the right side, I have an fa. I have an a is f. I am not allowed to universally generalize that statement. So note, you cannot universally generalize from a constant to a variable. You're only allowed to universally generalize a variable to another variable or the same variable. Okay? And there's a reason for this. Think about it. Just because there's an individual a that is an f, which is what's said on the right side at the top, there's an a that's an f, does not mean that everything in the universe is an f. So we're not allowed to generalize from a constant to a variable. So let's look at this example. All rockers are crazy people. All crazy people are out of control. Therefore, all rockers are out of control. Again, we can symbolize it this way. And remember, which should be familiar by now, since these are universal statements, they're going to be translated as conditionals. So premise 1 says for all x, if x is a rocker, then x is a crazy person. Premise 2 says for all x, if x is a crazy person, then x is out of control. My conclusion says for all x, if x is a rocker, then x is out of control. Now again, because all my statements are governed by a quantifier, I cannot use any of my rules of implication. So what I'm going to want to do is UI lines 1 and 2. Once we do this, we can then perform a hypothetical syllogism, but then in order to reach our conclusion, we're going to need to reintroduce the universal quantifier. And this is what UG allows us to do. So let's take a look at it. Here's our argument again. On line 3, what I'm going to do is I'm going to universally instantiate line 1. That allows me to remove the quantifier on line 1, and then I replace all bound variables with a like variable or constant. In this case, I'm going to do it with a variable because remember, my conclusion says for all x, Rx implies Ox. But since I'm going to have to use UG to reintroduce my quantifier, and I'm not allowed to UG from a constant to a variable, it would make no sense for me on line 3 to use a constant. Now I'm allowed to, but I'm going to use a variable because ultimately I've got to UG, and when I UG, I'm not allowed to move from a constant to a variable, so it makes more sense for me to just stick with a variable. So I UI line 1, I'm going to UI line 2, I'm going to use the same variable on line 4 that I used on line 3 so that I can use my rules of implication. So line 3 says if RY then CY, and line 4 says if CY then OY. So in other words, if I have a Y that's an R, then I have a Y that's a C, and if I have a Y that's a C, then I have a Y that's an O. So via hypothetical syllogism, if I have a Y that's an R, I have a Y that's an O. Now, in order to complete this thing, we've got to use our universal generalization. Now remember what that allows me to do. I'm going to be able to add a quantifier, and then I will change all my variables to match that quantifier. So in this case, since I'm trying to get all x, for all x, if x is R, then x is O, I'm going to choose variable x here, and I'm going to quantify with the universal quantifier x, so that I get for all x, if x is R, then x is O, from line 5 via UG. Problem solved. Now let's look at existential generalization. So let's say, for instance, I have an A that's an F or a Y that's an F. Now again, remember, my A is a constant and my Y is a variable here. I can then, much like universal generalization, attach a quantifier to it. Except unlike universal generalization, I'm not attaching a universal quantifier, but rather I'm attaching an existential quantifier. And also unlike universal generalization, I'm allowed to go from a constant to a variable. So existential generalization does not have the same restriction that universal generalization has. I can go from, if I have an A, or from an A that's an F, to there exists an X such that it's F. Or I can also go from the variable to a bound variable. So I can go either way. We can replace a variable or a constant with a bound variable. Hopefully you remember what a bound variable is. We talked about this in one of the previous podcasts. But what it means is that in this case, my x is bound because of the x that's in this quantifier. Over here, the same thing. This variable is bound by this quantifier. Okay? So I can replace this variable with a bound variable, and I can replace the constant on the left side with a bound variable. Now, because there's an individual A that is an F, means that there is at least one thing in the universe that is an F. That's what allows us to do what we did on the left side. Because I have an A that is an F, I know that there exists at least one thing in the universe that is an F. So let's take a look at an example. All bass players are legends. John Paul Jones is a bass player. Therefore, John Paul Jones is a legend. We can symbolize this as follows. For all x, if x is a bass player, then x is a legend. John Paul Jones is a bass player. Therefore, there exists at least one x that is a legend. There's an x that's an L. There exists at least one x, and that x is an L. Now again, we realize because line 1 is bound by that quantifier, in other words, the universal quantifier on line 1 is governing the entire line, we cannot use any of our rules of implication. So we're going to have to remove that quantifier. But look at our conclusion. Our conclusion is bound by an existential quantifier. So before we can get to the conclusion, we're going to have to reintroduce the quantifier. Specifically, we're going to need to reintroduce an existential quantifier. So let's take a look at how we go about doing this. First thing, though, if we instantiate the first line with respect to J, we can obtain LJ, that there is a J that's an L via modus ponens. Notice, if it's true that John Paul Jones is a bass player, then it certainly follows that there's at least one legend, namely John Paul Jones, that exists. And this last step will be accomplished by EG. So again, if you look at it, we notice that if it's true that John Paul Jones plays bass, then it has to be the case that there's at least one thing that's a legend. Because our first premise says for all bass players, or for all x, if x is a bass player, then x is a legend. So if it's the case that for all x, if x is a bass player, then x is a legend, and it's the case that John Paul Jones is a bass player, then there must exist at least one legend. So here's how the proof would look. On line 3, I'm going to universally instantiate line 1. Remember, I can UI lines that are governed by universal quantifiers. Again, though, it has to be the case that the universal quantifier is governing the entire line. So on line 1, we see that our universal quantifier is governing the entire line, so we're allowed to remove that quantifier, and we can replace those bound variables with either a constant or another variable. Since on line 2 I have the constant j, it makes sense for me to replace my bound variables, which are the variables attached to the b and the l, my x's, with the constant j, so that I can then perform modus ponens using my rules of implication, which is what we'll do. So on line 4, we can derive that there's a j that's an l via 2-3 modus ponens. Look, on line 3, it says if there's a j that's a b, then there's a j that's an l. Line 2 says there is a j that's a b. Therefore, line 4, there is a j that's an l. Now, in order to complete this, I've got to reintroduce a quantifier, because my conclusion is an existential quantified statement. And that's exactly what I do using e.g. I say there exists an x such that x is L. In this particular case, we know that it's John Paul Jones is a legend, so there exists at least one thing that's a legend. And that's what we've represented on line 5 using our rule e.g. Note, there's no restrictions on e.g. The operation can be performed when the instantial letter is either a constant, as in the above example, or a variable. So here's a broad rule for generalization. Introducing a quantifier immediately prior to a statement function, or another quantifier. Now, we're not to the point where we're going to be putting quantifiers on other quantifiers, so we want to maintain focus primarily on introducing quantifiers immediately prior to statements and statement functions. Second thing, replacing one or more occurrences of a certain instantial letter in the statement or statement function with the same variable that appears in the quantifier. So these are two broad rules for generalization. Now I want to talk a little bit about the difference between UG and EG. Hopefully you've already figured out some of them, but let's make it clear. So for UG, all occurrences of the instantial letter must be replaced with the variable in the quantifier. For EG, it's only the case that at least one of the instantial letters must be replaced with the variable in the quantifier. Let's look at an example to help clear this up. I will first show you two valid instances of using EG. So notice, on the left side, I have FA and GA. I am fully allowed to bring in or reintroduce a quantifier, in this case an existential quantifier, that binds both my variables, x and x here, and call that from EG. But I'm equally allowed to do what's done over here on this other side. Notice on the other side I've only changed the constant that's attached to f to the variable x. This constant attached to g stayed the same. So with existential generalization, I only have to instantiate at least one of my instantial letters. I only have to bound at least one of them to my quantifier. However, when doing UG, we're only allowed to go, or we have to bound every single instance. So notice on the left side, I add my universal quantifier y, and I change both my variables to y, so that the entire line is governed and bound by the universal quantifier. If you look to the right, the example in red is invalid. We are not allowed to do it to just part of a line. So for EG, we can do it on part of a line, but for UG, we've got to change our instantial letter to match our quantifier for the entire line. Otherwise, it's an invalid move. So back it up for a second. For UG, all occurrences of the instantial letter must be replaced with the variable in the quantifier. And for e.g., at least one of the instantial letters must be replaced with the variable and the quantifier. And that's exactly what we see here. Okay? So for UG, you've got to replace all instantial letters with the variable and the quantifier. And for EG, you only have to replace at least one. Moving on. Let's now look at existential instantiation. Okay, so existential instantiation works like this. Again, it has a restriction. On the left side, I'm totally fine. I can take the claim that there exists an X such that X is F, and I can remove the quantifier and replace the variable with a constant. Again, remember, my variables are lowercase letters X, Y, and Z, and my constants are lowercase letters A through W. So in the case on the left, what I've done is I've removed this quantifier, and I've replaced the variable with a constant. Now, on the other hand, if you look to the right, in the red writing, you'll notice that I am not allowed to remove my quantifier and replace my variable with another variable. So you are not allowed to existentially instantiate to a variable. You must existentially instantiate to a constant. So when doing EI, we're going to move from a bound variable to an unbound constant. You can never move from a variable to a variable. Okay? So the instance on the right side in red is not allowed. The instance in the white on the left is allowed. There's a further restriction as well. The existential name, and in this case I used A, must be a new name that does not appear in any previous line of the proof, including the conclusion line. Now, I'll make this more clear when we do some examples, but whatever constant you bring in after removing the quantifier, so if we look up here on the left, we see that we started with existential quantifier with the claim that there exists an X such that that X is F. We remove the quantifier and replace the variable with a constant. That constant, which in this case is A, has to be brand new. It cannot be the case that there has been an A on any line in the proof before I do this line, and it cannot be in the conclusion. Again, we'll make this more clear when we do some examples. So let's look at one. All rockers are legends. Some rockers are sloppy people. Therefore, some sloppy people are legends. We can symbolize this as follows. Remember, line 1 is a universal statement, so we will use a universal quantifier and translate it as a conditional. Line 2 is a particular statement, so we will use an existential quantifier and translate it as a conjunction. And my conclusion is a particular statement, so we will use an existential quantifier and translate it as a conjunction. So premise 1 says for all x, if x is R, then x is L. Premise 2 says there exists an X such that X is R and X is S. Therefore, there exists an X that is S and L. Now, if both quantifiers can be removed, the conclusion can be derived via simplification. Because remember, as long as my quantifiers are governing the entire line, as they are in both 1 and 2, I cannot use any of my rules of implication. So first thing I have to do is I'm going to have to UI and EI in order to use my rules of implication. Once I do that, then via simplification, modus ponens, and conjunction, we'll be able to get there. So we'll remove the universal quantifier on line 1 with UI, but in order to remove the existential quantifier on line 2, we're going to need to use our new rule, EI. Now line 2 states that there's something that is both R and S, and EI consists of giving this something a name. So let's take a look at it. Here is the problem. I have my first two premises and my conclusion. So first thing I'm going to do is I'm going to EI line 2. And well, remember, when I EI, what I can do is I can remove the quantifier and then replace each variable with a constant. But remember my other restriction. I have to use a constant that has not been used before. It has to be brand new, and it cannot be present in the conclusion. This is why I EI'd first. Because notice, on 4, I'm going to UI. So I'm UIing line 1. I'm removing the universal quantifier from line 1, and I'm replacing my variables with the constant d. Had I done that first, when I EI'd, I would not be able to use the same letter. Hence the reason that I EI first, because this is going to make my life a lot easier. I ultimately want to use my rules of implication, and in order to use my rules of implication, I need to have similar constants. So we want to EI first, and this is a good general rule to remember. If you know you're going to have to EI and UI, there's no reason not to just go ahead and EI first. That way you don't have to worry about using a constant that's already been used. So in this case, I EI first to get D, that's an R, and D, that's an S. Then I UI to get line 4. Now that I've done this, I can simplify line 3 to get there is a D, that's R. And now hopefully you notice that with line 4 and 5, I can do a modus ponens. Once I do modus ponens on line 4 and 5, that allows me to derive that there is a D, that's L. Now that I've done that, I can pull commutativity on line 3. So I'm going to flip that around, which then allows me to simplify line 7 to get that there is a D, that's an S. Now once I've done that, hopefully you recognize what we can do here. We can simply conjunct line 6 and line 8 to get that there's a D, that's an S, and there's a D, that's an L. Now, in order to finish this, I'm going to have to use EG. So I will now attach the E, or the existential quantifier, to line 9, and I will change my constants to the variable that is in my quantifier. Look at line 10, you'll see that it matches my conclusion, so my problem is complete. Now again, the big thing to take away from this is that when I'm using EI, I have to introduce a new constant that is not in any previous line nor my conclusion. That's the reason why we EI'd before we UI'd. Once I did that, we can just simply use our rules of implication and arrive at our conclusion. Okay, so it was just a simple move of simplification, then modus ponens, commutativity, simplification, conjunction, and then one of our new rules again, we use existential generalization to reintroduce our quantifier so that we can get what we're looking for in the conclusion. Let's look at some further examples. So in this case, line 1 says, for all x, if x is h, then x is L. Line 2 says, for all x, if x is L, then x is h. My conclusion says, for all x, x is h, if and only if x is L. Now remember, when we're using the biconditional, which is the triple bar here in my conclusion, what I'm telling you is that if I have an x that's h, then I have an x that's L. But also, if I have an x that's L, then I have an x that's h. So hopefully by now you realize that the strategy we're going to want to use here is to derive both conditionals. I want to get a conditional that says, if x is h, then x is L. And I want to get a conditional that says, if x is L, then x is h. Then what I want to do is conjunct the two of them together, and I can use my equivalence rule to derive the biconditional. So let's take a look at this. On line 3, I'll UI line 1, because remember, I can universally instantiate lines that are governed by a universal quantifier. Line 1 is completely governed by a universal quantifier, so I can remove my quantifier and replace my variables with another variable, or I can keep the same variable as I did in this case, or I can change that variable to a constant. But in this particular instance, since my conclusion ultimately is done with variables, I want to use variables. And in addition, since UG will not allow me to move from a constant to a variable, it would make no sense for me to instantiate to a constant at line 3. Thus, when I instantiate line 1, I remove the quantifier, but I'm just going to leave my variables as x. This is going to make things easier on me in the long run. You'll see why. So at line 4, we do the same thing to line 2 that we did to line 1. We universally instantiate line 2. I remove the quantifier, and I leave my variables as is. This is going to allow me to perform a rule of implication on line 5, which, as I explained previously, we're going to use conjunction. So notice on line 3 I have a conditional that says if x is h, then x is L. On line 4 I have a conditional that says if x is L, then x is h. On line 5 I've just conjuncted line 3 and 4. Now this allows us to use our rule of equivalence. Once I use my rule of equivalence, I end up with x is h if and only if x is L. One step's left, and that's just to reintroduce my universal quantifier. And in order to reintroduce my universal quantifier, I'm going to use UG, and the problem is complete. So look at line 7, look at our conclusion. You'll notice they match. And I was able to do this by using 2 UIs, then my rules of implication, then reintroducing my quantifier on line 7. Note, again, because we want to perform a UG on the last line of the proof, we instantiate lines 1 and 2 using a variable, not a constant. Remember, we are not allowed to UG constants. We are not allowed to universally generalize constants. You must remember that. Hence the reason on line 3 and 4 when I UI'd, I used variables and not constants. In addition, the variable we selected for use on line 3 and 4 is the same letter that occurs in lines 1 and 2. Now remember, I said we could have used any letter we wanted to. I could have used a Y or a Z, but it's not necessary. And in this instance, since we want to combine lines 3 and 4 and use them to derive line 6, and our ultimate conclusion has x as its variable, it just made sense to use the same variables in this instance. Okay, hopefully you get an understanding of what's going on with this rule. Let's look at another example. In this example, premise 1 says for all x, if x is A or x is B, then x is C. Premise 2 says there exists an x such that that x is A, and our conclusion says there exists an x such that that x is C. So again, I'm unable to use any of my rules of implication here, so I'm going to have to use my rules of instantiation first. I need to remove these quantifiers so that I can then use my rules of implication. Now again, remember, when we are existentially instantiating, whatever constant we bring in has got to be a brand new constant. It cannot be used in any prior line nor in the conclusion. So again, I'm going to begin by EIing line 2 so that I assure myself that I'm using a new constant. We'll choose M. It doesn't really matter what constant I choose, but in this instance we'll just choose M. So line 3 I derive from line 2 using EI. I remove the existential quantifier and replace my bound variable with a constant. Any constant of my choosing is fine, and in this case I use M. So now what I'm going to do is the same thing to line 1, except I'm going to use universal instantiation, of course, because line 1 is bound by a universal quantifier. So remember, existential instantiation can only be done to statement functions bound by existential quantifiers, and universal instantiation can only be done to statements bound by universal quantifiers. Again, note, we did the EI first due to our restriction that we have to introduce a new constant when we use EI. Now, to make things easier on us, I've used the same constant in line 4 from my UI of line 1. Again, I could have used any other constant I wanted to. And also, in addition with UI, if I wanted to, I could have used a variable. But since I want to be able to use line 4 with line 3, I've just chosen to use the constant letter M in line 4 as well. Now then, what we can do is we can take line 3 and we can use our addition rule. Now I have AM or BM. So I have there's an M that's an A or there's an M that's a B. Look at line 4. It says if there's an M that's an A or there's an M that's a B, then there's an M that's a C. Hopefully you recognize that we can use modus ponens right here. Cash out that there is an M that's a C. Now if we look at our conclusion, we'll know that it says there exists an X such that X is a C. Well, line 6 says there's an M that's a C. So what we can do is simply EG6, which means I'm going to add an existential quantifier to that line, and then I'm going to change my constant which in this case is m, to a variable that is in my quantifier. Now you'll notice line 7 matches the conclusion, and therefore we've solved the problem. But we need more. And I'm sure you're probably thinking, but we have enough already. Well, we do need a little bit more. So let's look at the following example to expose why we need a bit more. Line 1 says it's not the case that there exists an x such that that x is p and that x is not q. Line 2 says it's not the case for all x is r or x is q. And our conclusion says, therefore, there exists an x such that x is not p. Now, we can't use any of our rules of implication on this, and we can't instantiate. So if we cannot instantiate line 1 and 2, then we have no way of being able to solve the problem. Note, both premises have a tilde preceding the quantifier. In other words, they have a negation preceding their quantifier. So the main operator in these statements is negation. So neither statement can be instantiated. If we cannot instantiate them, then we cannot derive the conclusion. Remember, I can only instantiate lines that are governed by the universal quantifier. But in this case, since the negation is my main operator, it's not the case that my quantifiers are governing the entire line. So I'm not allowed to use my instantiation rules on these types of statements. So, take note. We can only perform UG, UI, EG, and EI on whole lines. And we can only use our rules of implication on lines that do not have quantifiers governing the entire line. So you might think of this as a case where the quantifier is the main operator. Example. Line 1 says there exists an x such that x is p and x is not q, and for all x, x is r or x is q. What is the main operator on this line? Hopefully you realize that the main operator is actually the dot. We're looking at a conjunction. The left side of the conjunction is an existential statement. The right side of the conjunction is a universal statement. But the statement as a whole is a conjunction. So my main operator is the dot. Therefore, I am allowed to use my rule of implication on this. I can simplify line 1 to give me what I have on line 2, which says there exists an x such that x is p and x is not q. And the reason I'm allowed to do this is because on line 1, my main operator is the dot. So it is not the case that my quantifier is governing the entire line. Therefore, I can use my rule of implication and simplify to get there exists an x such that x is p and x is not q. But you'll notice line 2, my statement is governed, the entire line is governed by the existential quantifier. So I cannot use my rule of implication on line 2. But what can I do? Use my rule of instantiation. Now, since line 2 is governed by an existential quantifier, we can use existential instantiation and remove that quantifier and replace the bound variables, the x's, with a constant that has not been used and is not in my conclusion. So note, line 1's main operator is the dot, so we can use our rule of implication, but we are not allowed to use EI or UI. The whole statement function on line 2 is governed by the existential quantifier, so we can use EI on it, but we cannot use our rules of implication on it. Pay attention to what's going on in this particular slide and make sure you understand when you're allowed to use your rules of implication and when you are not. One more thing. You can use rules of replacement on lines governed by a quantifier. So unlike the rules of implication, rules of replacement can be used on lines governed by a quantifier. So for example, if I have this statement, for all x, it is not the case x is h and x is g. I can use my rules of replacement on this line. So, for instance, I can use De Morgan's, and I can convert my negated conjunction that's on line 1 to a disjunct using De Morgan's. Remember, De Morgan's would tell me that if it's not the case X is H and X is G, then it is the case that not X, that X is not H or X is not G. Okay? So we can use our rules of replacement, but we cannot use our rules of implication on lines governed by quantifier. So what you see in this example is perfectly legal. So again, remember, rules of implication, not allowed to use them on lines that are governed entirely by a quantifier. Rules of replacement, you can use on lines that are governed by a quantifier. So let's go back to the example. We cannot instantiate any of the lines, and we cannot use any of our rules of implication, so we cannot derive the conclusion. So we're going to need one more rule. Change a quantifier rule. Sometimes you'll hear me call it exchange of quantifier. Sometimes you'll hear me call it quantifier exchange. It's represented by capital letter C, capital letter Q. Change a quantifier rule or a quantifier exchange. So to get started on this, we need to look at 4 logically equivalent expressions. This one says, on the left side, for all x, x is f. Now these 4 dots, they represent logically equivalent. So that means that this statement is logically equivalent to this statement. So the universal statement on the left, logically equivalent to the existential statement on the right. So the universal statement on the left, again, says for all x, x is f. The existential statement on the right says it's not the case that there exists an x such that that x is not f. We'll go through each one of these individually, but let me just kind of move forward for a moment and show you all 4 of the logically equivalent expressions, and then we'll go through each and every one on its own. So the second one says it is not the case for all x that x is f. It's logically equivalent to there exists an x such that x is not f. My third one says there exists an x such that x is f is logically equivalent to it is not the case for all x that x is not f. And last but not least, my fourth one says it is not the case that there exists an x such that x is f is logically equivalent to the claim for all x, x is not f. Now, I know that this might seem a little bit cloudy right now, so what we're going to do is we'll go through each and every one of these one by one, and hopefully you'll see how it is that they actually are logically equivalent. They really are saying the same thing. So let's look at the first one. In this first claim, what I've got is for all x, x is f, is logically equivalent to the claim that it is not the case that there exists an x such that x is not f. So for the moment, let's just claim that what f stands for is fantastic. This will allow us to make things easier. And we'll stick with this through all the examples. F will just mean fantastic. So our first statement on the left up top, our universal statement, just means everything is fantastic. On the right side, what's being said is that it's not the case that there exists something that is not fantastic. So notice, if everything is fantastic, then of course it's also the case that it's not the case that something is not fantastic. These 2 statements are logically equivalent, which means they're interchangeable. So think about what's being said. If everything in the universe is fantastic, then there cannot be one single thing that exists in the universe that is not fantastic. So we can substitute the statement for all x, xf, with the statement, it is not the case that there exists an x such that that x is not f, and vice versa, because they are logically equivalent. Again, think about it. If everything in the universe is fantastic, then there cannot be one single thing that exists in the universe that is not fantastic. And that's what the second version says. If we look at our existential version here, or our negated existential version, it says it's not the case that there exists an X, that X is not F. In other words, every single X is F, which is exactly what the universal statement says. So let's look at the second one. This one says it's not the case for all X that X is F is logically equivalent to there exists an X such that X is not F. So again, the statement on the left says it is not the case that everything is fantastic. And this is equivalent to the statement on the right, which says something is not fantastic. Look, there exists at least one thing in the universe that is not fantastic. What does that mean? Something is not fantastic. Okay? The one on the left says it is not the case that everything is fantastic. So think about what's being said. If it's not the case that everything in the universe is fantastic, then it is the case that at least one thing that exists in the universe is not fantastic. So we can substitute the statement, it is not the case for all X, X is F, with the statement, there exists an X such that that X is not F, and vice versa, because they are logically equivalent. Notice they're saying the exact same thing. If it's not the case that everything in the universe is fantastic, then it must be the case that at least one thing exists in the universe that is not fantastic. So we can interchange these two statements back and forth. Let's look at the third one. The statement on the left says there exists an X such that X is F. The statement on the right says it is not the case that for all X, X is not F. So what's the statement on the left actually saying? It's saying something is fantastic. There exists at least one thing that's F. So there's at least something that's fantastic. And this is equivalent to what's being said on the right. On the right, what's being said is it is not the case that everything is not fantastic. So what's that telling me? There's at least something that is fantastic, because what's not the case is that everything is not fantastic. Think about what's being said. If it is the case that there exists something in the universe that is fantastic, so we know there's at least one doggone thing in this universe and it's fantastic, then of course it is not the case that everything is not fantastic, because we know there's at least one thing that is fantastic. So we can substitute the statement, there exists an X such that X is F, with the statement, it is not the case for all X that X is not F, and vice versa, because they are logically equivalent. They are literally saying the same thing. Let's move on to the last one. So in this instance, what we have on the left side is the claim, or the statement, that it is not the case that there exists an X such that X is F, is logically equivalent to the claim that for all X, X is not F. So, the statement on the left just says it is not the case that something is fantastic, which of course is going to be equivalent to everything is not fantastic. So, on the left side, what that statement says, or what it translates as is it is not the case that something is fantastic. On the right side, our universal statement says everything is not fantastic. For all X, X is not F. So think about it for a second. If it is not the case that something is fantastic, then of course everything is not fantastic. Think about what's being said. If it is not the case that there exists something in the universe that is fantastic, then it is the case that everything is not fantastic, right? If it is not the case that there exists one single thing in the universe that's fantastic, then that just means that it is the case that everything is not fantastic. So we can substitute the statement, it is not the case that there exists an X such that X is F, with the statement, for all X, X is not F, and vice versa, because they are logically equivalent, and they are literally saying the very same thing. So let's go back to the example. Again, look at what I have. Remember, I cannot instantiate lines 1 and 2, so I'm not going to be able to derive the conclusion of this. So let's take a look at the proof for this example. Here we go. Now this is a bit of a complex proof, so try and follow along. What we need to do, since we cannot instantiate lines 1 or 2, is we're going to have to use our new rule, which is the quantifier exchange rule. Now remember, line 1 says it is not the case that there exists an x such that x is p and x is not q, which just means the same thing is that for all x, it is not the case that x is p and x is not q. Again, as I discussed in the prior examples, if you look at what's being said, you'll see that what 1 and 3 are saying is the exact same thing. Because 1's just telling us it's not the case that there exists something in the universe that is both p and not q. And what x is telling us is that for everything in the universe, it is the case, not p and not q. Okay? Number 1 says it is not the case that there exists something in the universe that is both p and not q. So there's not one single thing that exists that is both p and not q. 3 is saying for everything, for all x, it's not the case that x is p and x is not q. It means the exact same thing as line 1 does. So now we can do the same thing to line 2. Okay? Line 2 originally said it's not the case that for all x, x is not r or x is q, which just means the same thing as that there exists an x such that it's not the case that x is not r or x is q. Now notice what I've done. Now that I have the change of quantifier rule, I'm able to convert my statements on line 1 and line 2 to statements that are bound by the quantifiers. So what does that mean? Now that 3 is bound by a universal quantifier, I can use ui. And now that 4 is bound by an existential quantifier, I can use EI on it. So what will we do? We will use EI. And again, one of the reasons why I'm using EI first is because we want to avoid our problem. Remember, EI has a restriction that says I have to use a constant that has not been used before and is not my conclusion. A is not my conclusion. A has never been used. So I'm going to start with my EI so that I can avoid the problem of having that constant already in play. So we just EI line 4, which again just simply means I remove my quantifier and I replace all my variables with the constant of my choosing, as long as that constant is new and is not in my conclusion. Now hopefully you guessed we will UI line 3. So again, I remove my universal quantifier from line 3, and I'm going to change my variables in line 3 to match my constants in line 5. So I'm going to use the variable a in line 6 as well. Again, the reason why I'm going to do this is because ultimately I want to use some of my rules of implication, and if I have the same constants, then it'll make it much easier for me to do this. Now that I've EI'd and UI'd, I can start using some of my other rules. So if we take a look at line 5, we should immediately recognize that we can use De Morgan's on it. So from De Morgan's on line 5, I can convert my disjunct on line 5 to a conjunct on line 7, which would give me not the case that A is R, and not the case that A is Q. Then I can double negate line 7 so that I got A is R and A is not Q. This should be pretty simple at this point. You should be familiar with these sorts of rules of replacement. It's just like it was in propositional logic, right? Now that I've removed my quantifier, I'm really just doing the same things that we did in propositional logic. Next thing I'll do is I'll De Morgan's line 6. So on line 6, I'm going to convert my negated conjunct to a disjunct using De Morgan's. So now what we can do is just do double negation off of line 9 and arrive at line 10 with A is not P or A is Q. Because remember, just not Q means the same thing as Q. So we use our rule of replacement double negation, and we end up with A is not P or A is Q on line 10. Hopefully, you begin to see a strategy developing here. If we take line 8 and do commutativity on it, so we flip it around, so that I've got A is not Q and A is R. We can then do simplification on line 11 to get A is not Q. Now notice, once we do this, what we can pull is a disjunctive syllogism on line 10. So take a quick look up at our conclusion. Our conclusion ultimately says there is an X such that X is not P. Now take a look at what we have going on line 10. I have there's an A that's not P, or there's an A that's Q. On line 12 I have there's an A that's not Q. So if it's the case on line 10 that A is not P or A is Q, and it's the case that A is not Q, then it must be the case that A is not P. Okay? But first thing, we have to do a commutativity on line 10. So we've recognized our strategy, and then we do our commutativity on line 10, allowing us to perform the disjunctive syllogism I just described. Then we can do it 12 and 13 disjunctive syllogism to get there is an A that's not a P. So notice, once I recognized what strategy I needed, all I had to do was commutativity on line 10, where I flip it around, thus allowing me to take line 12 with line 13 and derive my A is not a P. Line 13 says A is Q or A is not P. Line 12 says A is not Q, so therefore A must be not P. So I'm almost done with my problem at this point. All I need to do is to add my quantifier, which in this case is an existential quantifier, so we're going to use EG, and we're going to add a quantifier, and we're going to replace our constant with the variable that's in the quantifier. This matches up with my conclusion, so this problem is complete. And hopefully you get an idea at this point how it is that CQ works. So notice, anytime that I want to transfer or switch around one of my statements that has a quantifier in it and CQ is applicable, then I can do it. Lines 1 and lines 2, I couldn't do any sort of rules of implication on it, and I wasn't able to instantiate them. So the only thing I could really do was CQ. So after I CQ'd on line 3 and 4, hey, we're right back in business with our normal thing. We can just EI, UI. We do a few rules of replacement with De Morgan's and double negation. Then we flip a commutativity, and then just a couple rules of implication, and then an EG at the end. And bada boom, bada bang, we got our answer. So I hope this is helpful. I'm going to do more videos with more examples using all the rules next. So after this particular podcast, if you check out the next video, it will be of me doing more proofs using all of the rules. Okay? So I hope that you understand this. I hope that this podcast helped. Be sure to check out the next video as well. Predicate logic, it is your friend.